OK, let's begin. Today is the last day of Epoch 3. So the third part of the course, that's where we're learning all these slick shortcuts for taking derivatives. And then in Chapter 4, Epoch 4, we'll start putting some of them to use. You'll see some of the applications of derivatives in different settings. So today, we'll do 3.7 and 3.9. We're skipping 3.8 and 3.10 from Chapter 3. Homework help. Is this Mackenzie's time? I don't know why I am incapable of remembering that, but apparently I am. And then Casey later this evening, tomorrow morning, 11 to noon, Corey, and I'll be available 2 to 3. And I should be able to stick around certainly a little bit longer if need be. The homework this week is long and a little repetitive. I mean, this is sort of trying to build muscle memory for doing certain types of things. So it's sort of repetitive by design. One big warning is that the answers in the back of the book will often look different than your answers, because the back of the book simplifies things in ways that often to me actually don't seem particularly simple, but that's how they do it. And then sometimes they're assuming you're using the quotient rule, which puts the answer in a particular form, whereas if you use the product rule and the chain rule, the way I like to do it, it's in a different form. It's all the same. It's math. They're all the right answers. So I think a lot of some of the angst from the homework help last night was people were actually doing it correctly, but they didn't realize that their answer was the same as that in the back of the book. So if you're a little unsure about that, you could spend some time trying to show that the two answers are equal. If that's satisfying for you, go for it. If not, you can always just check with one of us. Often we can sort of take a look at it and right away see, yep, that's right, no problem. Or you could query Wolfram Alpha, because Wolfram can do derivatives also. But Wolfram also might put it in an unusual form. Let's see. So one other announcement sort of thing, which is for the last couple weeks of the term, I'm going to have to shift around my Wednesday help time. So I've got something later in the evening, 7:30 in Ellsworth, so I can't do that time. So I was going to propose just shifting more like 5 to 6 on Wednesdays. But I could also, I'm now free Tuesday evenings, whereas I wasn't free Tuesday evenings before. So we can see if this is going to totally, I know some people, this was the main time, or that used to be the main time you went to, and if this is crummy, let me know. I could add a Tuesday, I think most of the time a Tuesday evening sort of thing. So anyway, the schedule is going to be slightly different. Sorry about that. Any questions, announcements? OK. All right. So there are 2 topics for today. And the first topic is this thing called implicit differentiation. And I guess I should say about both of these topics, how to put this? I sort of want to lower expectations. We're sort of like, whatever the climax and the peak was of Chapter 3, it's not going to be today. It was sometime in the past. So we're sort of decrescendoing, doing a few other topics that are important, but maybe not the most, the sort of highest peak of action. And my suspicion is that the first thing, implicit differentiation, you will find a little bit confusing and wonder why we're doing it. And then the second topic you'll find almost weirdly simple and wondering why we're doing it. So anyway, this is going to be maybe a little bit weird. I never know quite how to motivate these topics. So I guess my attempt was to demotivate it to lower everybody's expectations, and then we'll be able to exceed them. That's my plan. All right. So let me say a little bit about implicit differentiation. It's an important topic. It's something that probably won't play a huge role later on in this course, but it's a really important Calc 1 skill that when it's useful, it's incredibly useful. All right. So implicit differentiation starts with this idea of an implicit function. And before we talk about implicit functions, I need to talk about explicit functions, which are nowhere near as racy as it sounds. All right, so here's an explicit function. Explicit function. So that might be something like y is 4x squared plus sine x. So a function is a relationship between inputs and outputs, between x's and y's. And here, this is just explicitly telling you what that relationship is. What's y? It's 4x squared plus sine x. You tell me x, there's one and only one y. So it's an explicit function. We know exactly how that relationship works. We could also have an implicit function where there's a relationship that's implied but not directly stated. And an example of that might be this. So in this situation, x and y are in a relationship because you can think of x determining y, you can think of y determining x, but it's not sort of an explicit relationship like this where all the x's are on one side, so you can just plug in x's and get your y. So this would be an implicit function of, we'd say y is an implicit function of x. Here, y is an explicit function of x. Yeah?
Why would you just change it so that x is there on one side?
Ah, OK, great question. So in this case, you could. Let's see. You might have situations, and you will on the little practice sheet we'll get to in a little bit, where x and y are so tangled together, the relationship is so complicated that it can't be rendered explicit. In this case, you can untangle them, although it's a little bit of a different deal than we're used to. So if you were to plot this function, and maybe you should even put function in quotes, this relationship. Anybody have a guess what this would look like? Yeah. It would be a circle almost, like that, with a radius of 1. So you can think of this as like giving the coordinates of all points that are a distance 1 from the origin. So if we do what Heather was wanting to do entirely reasonably, we could say, well, y squared is 1 minus x squared. And then y would be plus or minus 1 minus x squared. So when you take the square root, you have a plus or minus corresponding to the top half and the bottom half of this semicircle. So strictly speaking, this actually isn't a function because the same input can have two outputs. All right. So let's suppose we wanted to know the slope when x is a quarter. So what is the slope if x equals 1/4? So that might be something we would want to know in some context. And what I want to do is do this two different ways, implicitly and explicitly. So we'll do it the explicit way first. And let's say I'm interested just in this top value here. There's a tangent line. I want to know what's the slope of that tangent line. All right. So if you were worried there weren't enough chain rules in your life, you'll get to practice the chain rule right now, just in case you were missing it. So the derivative of something to the half is half of something to the minus half. And then the derivative of this something, that's a minus 2x. All right, let's see. I'm going to need a calculator assistance in a moment. I could rewrite this as minus x on 1 minus x squared. And so if I plug in x equals a quarter, oh, sorry, this is y prime here. So I just did the thing I told you not to do, right? Which is just like keep equal signs going down. See, that's why, because it's confusing. You forget what the derivative is and what isn't. All right, so here's y prime as a function of x. We found the derivative. We brushed up against, got to hang out with our friend the chain rule for a little bit. And so now we can plug in a quarter, and we'll get some number. And Lexi is furiously typing away. Nobody else is typing away, so it's all OK. Now some people are helping Lexi. Should be negative.
I got negative
0.24. That seems reasonable to me. Oh. Minus 2.6? OK. Minus 2.6.
Oh, no, 0.3.
Oh, 0.26. 0.26. OK, that seems 0.26. OK. So we'll expect a here's the tangent line, this thing in orange. It's got a negative slope. So that seems like a reasonable number. So this is explicit differentiation, because we wrote y explicitly as a function of x. So what I want to do now is implicit differentiation. And you can decide which you like better. Sometimes you sort of have to do it implicitly, but this time both are doable. So all right. So implicit differentiation. And the thing here is that we're going to view y as a function of x. So so this is an implicit functional relationship. It says x and y depend on each other. And so to remind myself of that, I'm going to just remember we're viewing y as a function of x. So what we'll do is we don't solve for y. We just take the derivative of both sides of this equation. So let's do that term by term. So the derivative of x squared is 2x. Excellent. And the derivative of 1 is 0. So this is a term we're going to have to think about. So what's the derivative of x? We say, what's the derivative of x squared? Well, we just did that. So the derivative, all right, the derivative of y squared is 2y. But y isn't x. Y is a function of x. So really, we need to think of y as an inner function. Yeah, this is when it always comes off the rails. Okay. All right. So, all right. So if you had to do all right. So if you had to do this, sine x squared, an inner function, sometimes called blah, sometimes called whatever. So the derivative of blah squared is 2 blah. times the derivative of the inner function, which is cosine. So that's your old friend, the chain rule. What if you had the inner function was called g? What would you do then?
G times gx times the derivative of g.
Yeah.
Okay.
So that's just replacing, right? So you had a sign here, 2 sine, now it's 2g. This cosine was because it's a derivative of the inner function, and that's g. If you had the inner function was called y, well, the derivative of blah squared is, I mean, it's always 2 blah. And then the derivative of the inner function. So I sort of think of implicit differentiation as chain rule in disguise. We don't think of y as an inner function, but if it's in this implicit context, it is indeed an inner function because it depends on x.
Right, Dave, what
Yep.
about y prime x?
Here?
No.
Oh, you can definitely write it like that if you want as well. Right, because like sometimes we write y is blah, blah, blah. You could just as well write y of x is blah, blah, blah. All right, so my sense is that not everybody is perfectly happy with this, but my impression also is, or my experience suggests that I'm not going to be able to make you perfectly happy with this in the next couple of minutes. So I want to keep going with this example, and you'll probably do a few more examples, and you'll start to feel a little bit happier about this. So we end up with this expression. And our goal is to find a slope. So now I can isolate y prime. So I'm going to, let's see, what do I do? I've got 2y, y prime is minus 2x. The 2's cancel. I divide through by y, and I get y prime is minus x over y. All right. So we now have 2 different expressions for y prime, the slope of this function or this relationship. I like this because it's simple, no square roots. Minus x over y. This is nice because it's explicit. It's a little more complicated, square roots and stuff, but it's explicit because you just have to know x. To figure out this one, you have to know x and y. So let's see how you would do that to get a value for y prime, and you'll see, with any luck, that we get the same number, and that will be at least relieving, if not comforting. All right, so let's see. Can I erase this stuff here? All right. All right, so x equals a quarter. You might wonder, well, what's y when x is a quarter? Well, let's see. We can go here and figure that out. Y is 1 minus a quarter squared square root. And again, a calculator will be useful. A quarter squared is a 16th. 1 minus 16th is 15/16 is, I don't know, it's a little less than 1. Point 9-ish. 0.97. So then we've got this nice implicit formula for a derivative, minus x over y. If I do that, or if you do that, there we go. Yeah, OK. So, right, we get the same. We're just finding the slope. And there are just two different paths to it. We've been using this path all along. But there are times when it's actually a lot easier to do implicit differentiation than explicit differentiation. Casey is nodding enthusiastically. It really is. And the key is to remember that when you have an implicit function, y is actually a function. So you think of it as y of x or g of x or something like that. So I think we should launch into some examples. And impressively, the first two problems have typos in them, because someone walked into my office while I was typing them, and then I just kept typing them while I was talking, and then I didn't look at what I was typing. Anyway, so another thing that I do that you shouldn't do. So I'm going to put corrections on the board, and then we'll just launch off into this, and we'll see how it goes. All right, let me say a few things. People are predictably confused because this is a little bit confusing. So let me say a few things, and then you can go back to being slightly confused, but hopefully the confusion will start to diminish. So first of all, keeping with the inadvertent theme of me doing things I advise you not to do. So I had this over here when I started doing this initial example, and I went from this step to this step. And I said I'm taking the derivative of both sides. But then if you just have this in your notes, or you write this on the board, this actually it's not immediately obvious what happens to go from here to here. So instead, like when I started doing this one, I said x squared plus y squared equals 16. And then what this says in symbols is I'm taking the derivative of the left-hand side and the right-hand side. I definitely should have written that down over here, because then your notes will make a ton more sense to you. So like I say sometimes, like little things like that in your notes can make the difference between something being incredibly helpful or very mysterious a week or an hour or a month from now. So like writing down what you're doing to both sides of an equation, it doesn't take a lot of ink or chalk. It can be very helpful. So anyway, so I didn't do that here, and a couple people were confused. They weren't like, how did we go from here to here? Had I written it down, then there wouldn't have been confusion. All right. So now I'm making it clear. I'm taking the derivative with respect to x of both sides. All right. So how does 16 depend on x? Well, it doesn't. It's just 16. It is going to be 16 no matter what x is. So it's 0. Derivative of a constant is 0. Here, derivative of x squared with respect to x is 2x. But here, this term, I could write it like this. How does y squared depend on x? Well, this is a sort of chain rule sort of situation. There's this function y squared, but y itself depends on x. So y of x is an inner function, just like sine of x might have been. So this is going to be 2y. Derivative of blah squared is 2 blah, times the derivative of the inner function, which is y prime, dy dx. So the answer for this ends up being just the same as the other one, which is kind of cool. Shall we tackle this one? All right. So let's see. The derivative of 0 is definitely 0. How does nothing depend on x? I mean, it doesn't. All right. Derivative of x squared, that's just 2x. Nothing implicit there. That's very explicit. Now I've got this one, a y and an x. And remember that y is implied to be a function of x. So they're both functions of x. And they're multiplied together, so that's a product rule situation. Bless you. So I take the derivative of the first one, leave the second one alone. Derivative of x is 1. I leave y alone, so that's just y. Plus, I leave the first one alone, x, and I take the derivative of y, and I don't know what that is. That's what I'm trying to find out, so that's just y prime. So both of these terms come from that term. The derivative of y with respect to x, that's what I'm trying to find out. That's y prime. And the derivative of 17 is 0. So at this point, we've implicitly differentiated. You could solve for y prime if you want, but the implicit differentiation is done. All right. Are there questions on this? Are there explicit questions as opposed to an implicit sense of unease? I mean, if you're still a little uneasy with this, that's OK. It takes a little, it'll take a little while sort of to get oriented to this, but it will definitely come. So let me say one more thing about problem 2. So this is what I was trying to get at in problem 2a. So here's another implicit function. Y and x are in a relationship, but they're tangled up, and it's not like all the x's are on the other side. So in this situation, it's actually not really, it's technically possible, but it will not be difficult to convince you that you don't want to solve for y. So OK, if you solve for y, there's a cube here, so this is a cubic function. So OK, if this were a square, you'll have to use a quadratic formula. And I'm guessing you're not huge fans of the quadratic formula. OK, so you would love the quadratic formula compared to the cubic formula, which you haven't even seen before because nobody ever uses it because it's like 4 or 5 lines long. So it would be a real mess to solve for y. But the good news is if we want to differentiate, we don't need to solve for y. We can just differentiate implicitly. OK, so 2a was to convince yourself that you don't want to solve for y. I just convinced you. But anyway, for now we can do b, c, and d, where we actually carry out that implicit differentiation and then do some stuff. And we don't ever have to solve a cubic, which definitely should be among your life goals. Never have to solve a cubic equation. All right, so give this a try, and then we'll move on to 3.9. All right, so let me say a few things about this. So here we have one of these implicit functions. It can be helpful sometimes to make a graph. So I asked Wolfram to make a graph. It is not obvious to me that this implicit relationship between x and y, when graphed, has this form. But it's, I don't know, it's still nice to sort of have a picture. So then, just to reiterate, we don't want to solve for y because it would be just absolutely heinous to do, because you'll need to solve a cubic. So instead, we just implicitly differentiate. So here I am doing that. And I, for this step, decided to write y as y of x, just as a reminder that y is actually implicitly a function of x. If that's not helpful for you, don't do that. You can just write it as y, either way. So then, taking the derivative of both sides, I'm asking how this thing varies with x. And so it's a chain relationship. Y is getting cubed, but x is getting wide. So the inner function is y. So x first gets wide, and then it gets cubed. So we just chain rule that. Derivative of whatever cubed is 3 times whatever squared, times the derivative of the inner function. We don't know what that is. That's what we'd like to find out. So we just call that y prime. Here we need to use the product rule, like we did there. So derivative of the first one, leave the second one alone. Derivative of x is 1. Plus, leave the first one alone, take the derivative of the second. The derivative of the second is just y prime. So here we've implicitly differentiated. And now to solve for y prime is no big deal. Just collect terms, divide through, and we get this nice equation for y prime. It's in terms of x and y. It's an implicit relationship because there's y here as well as x, but that's fine. It's still a useful thing. So then I asked you just to check that 7 and 2 are a point on this curve. And a point on the curve means that it makes this equation true. So if you plug in, and you remember how minus signs work, which apparently I didn't when I was cooking up this problem, you decide, yes, this really is this. So then, all right, I've got an x and a y that's on the curve. I can figure out what the slope is at that point by plugging into this formula. And here I am doing that. And again, once I remember how minus signs work, I get that this is plus 2/5. So it's a small positive slope. And if you look at the curve, this is the top branch of that sideways parabola. Oh, I left mine over here. You can see that the slope is indeed positive, and it looks sort of small. So an answer of 0.4 seems reasonable. So this is implicit differentiation. In my experience, it's not something at least in my math life, it's not something I encounter every day or that frequently. But when you do encounter it, it's incredibly, incredibly useful. Because it would be solving this the explicit way would in theory be possible, but would be blackboards and blackboards full of work. So it's a very useful thing when it's useful. And it's important enough that it's worth spending 55 minutes on in class, which we've now done. So not a huge emphasis of the course. There'll be maybe a half dozen problems on this to practice it a little bit. But that's that. So let's move on to 3.9, which I think you will find less disorienting. So I feel like implicit differentiation always feels to me not really difficult. It's the same rules, but it's a little disorienting because now you just have to be on your toes. Wait, what's a function of what? Is this a function of x, of y, and so on? All right, so 3.9 is about local linearization. And this is an idea that we've been using implicitly and explicitly all along, but is worth just doing a little bit more with. What's the official name of 3.9? Linear approximations and the derivative. All right, so let me say a little bit about this, do a couple practice problems. All right. OK, so here's a curve. And for lack of a better name, we'll call that f of x. And then that will be a particular point A that we might be interested in. And the whole point of really this entire course so far is that somebody might say, well, what's the slope of this? And you'd say, well, that's crazy. Slopes are for lines, not curves. But if we zoom in really close, which I'd probably put this too high on the board for, I was a little taller, The curve starts to look like a line, and then you say, oh, it really is just a line. No big deal. I know about slopes of lines. It's rise over run. So that's what the derivative is. That was sort of back in chapter 2. We've been doing all this crazy stuff, but that's all we're doing is pretending curves are lines and finding the slope of that line. So there's the tangent line. All right. So if we're here, we're at our y value is f of a. The input is a. The point of the curve is f of a. If I go over, if I run this distance, so this is x. If I run a little distance, I'm going to rise, and my rise is determined by the slope. And the slope we know is just this. So this is sort of like saying rise equals slope times run. It's not sort of like saying that. It is saying that. So we've done stuff with tangent lines before. This is just a sort of more direct formula to get to a tangent line. Bless you. So the idea is that the tangent line is actually a pretty good approximation to the function itself. So this is the function itself that might be some strange curvy thing. But if we're near the point A, the tangent line is pretty close to the function. So if I'm just like right in here, that's pretty good. So this formula, to use this formula, you just need to find the derivative at point A, and then you just write down the tangent line approximation. And this also turns out to be incredibly useful, and you do all the time. And I always have a hard time convincing people of this, and I'll probably have a hard time convincing you as well. Because like the situation is you already have this nice formula for this function with all the curves in it and everything, and that's awesome. But it can be really difficult to work with that curvy function. So if instead you take that curvy function and you turn it into a line, then it's a lot easier to work with. So again, it seems like a really weird thing to take, you have a formula and you turn it into a simpler formula. That's not exactly true, but one does it actually all the time in other areas of math. And the formula isn't hard to use. So I think we should just yeah, let's just start with a few examples, and we'll see how they go, and we'll take it from there. All right, so we have about 10 minutes left, and let me go through these, and we'll see if this answers your question. If it doesn't, that's good. So let's start with the first one, since that was first. So the function is x to the minus 1. The derivative of x to the minus 1 is minus x to the minus 2. So here's the formula for the tangent line approximation. So it's that formula there, but a is 2. So I just plug in 2. Then I need to evaluate the function at 2. X minus 1 is 1 over x. I need to evaluate the derivative at 2. It's that guy there. And there it is. That's the tangent line approximation near x equals 2. So if I were to plot this line, put it in y equals mx plus b form, it would be this orange line. So the white curve is 1 over x. And the orange line is a tangent line, label this point, at x equals 2. So we can see right away that the tangent line is close when you're near to 2. It's far away when you're far away from 2. But that's why it's called local linearization. It's valid only locally. And that the orange line is below the white line. So it'll be an underestimate. And that's what we can see numerically. So here, I'm using the tangent line approximation to approximate the function when x is 2.1. So I'm plugging 2.1 not into the original function, but into the tangent line approximation. And I did that here. And that actually was a relatively simple calculation. I was able to do it in my head. So I always feel a little lucky when I'm able to do that. So I guess this doesn't have a question mark anymore. That's been affirmed. It's 0.475. So how good is that approximation? Well, let's see. Well, let's do the exact value. If I plug in to this formula, not the approximate formula, but the exact formula, I get 0.476. That's pretty good. So we're 5% off x. All right, so this is exact at x equal 2. 2.1, I'm 5% away from 2. You know, it's a reasonable sized step, but I'm still really close to the, this approximation is still really close to the exact value. This 2 and 2.1? 0.1, 0.1, 0.5. It's let's just say it's something, yeah. So going from 2 to 2.1 is you're strayed pretty far from 2, and you're still pretty close. The tangent line and the exact are still pretty close. So you know, this, if nothing else, this trick can be useful for evaluating things like this quickly in your head and getting, without having to do long division, getting reasonably close. All right, so that's, hopefully you think, well, that's kind of neat. Yeah, all right. And again, if this were a much more complicated function that you know, with, and all you ever cared about with what was going on near x equals 2, it might really be to your advantage to just replace the complicated function with the linear function. All right, so here are a couple more. This is problem 2, not B. So sine theta, derivative of sine theta is cosine. And then I plug into the tangent line approximation formula. And I get sine 0 plus cosine 0 times x. And sine 0 is 0. Cosine 0 is 1. So this is sine. Oh, I turned an x into a theta, or a theta into an x, didn't I? Sorry. So sine theta is approximately theta for small theta. So in physics, sometimes people talk about the small angle approximation. Sine x is approximately x. This is where that's from. It's only true in radians. One person was nodding, which is actually one person more than usually nods. So that's great. And so you can sort of see that. Where'd my orange chalk go? You can see that here. The scale is off a little bit, but this orange line is a tangent line, and this would be the equation for that tangent line. Just y equals x. For cosine has a maximum at 0, so its derivative is, I mean, the slope of this tangent line would be, it is neither going up nor down. 0, yep, okay, right? So that tells you right away, actually, that the slope, I mean, this is a boring tangent line, but that's OK. Sometimes boring is good. The tangent line approximation is just pretend it's constant at 1. So that's also sometimes used as a small angle approximation for cosine. And this is just sort of cranking through that stuff. And then this is doing the same sort of thing, but with e to the x. This one you have to use a chain rule. You bring down a k. Remember that e to the 0 is 1. And you get that e to the kx is 1 plus kx for small x. So I'm hoping perhaps that this it's relatively straightforward to just plug into this formula. And it seems maybe silly, like why would you ever want to do this? But not that this is a good answer, but trust me, you do want to do this sometimes. But the good news is that it's not a difficult thing to do. So again, there'll be a few practice problems on this, maybe which will help to illustrate the utility of it. But anyway, definitely a good thing to know. So I can stick around if there are some homework questions, which there may be. I don't need to split right away. And then the homework help time tomorrow.